So in this example problem, we have a crate has a weight of 40 pounds. Right? We were given the information that this crate is supported by 3 cables: a cable from point A to point D, a cable from point A to point C, and a cable from point A to point B. And we're given the dimensions of where those cables are anchored to supports at C, B, and D. And we're asked to determine what are the forces within each cable. So our first step we're going to do here is we're going to draw the free body diagram. So in this case, we'll have our point A at the center of our free body diagram. Alright, we'll draw our X, our Y, and our Z axes, and then we'll draw our weight vector, and then we'll draw our 3 cables. So we'll do TAD. We'll do our cable that goes from point A to point C. And we'll draw our cable that goes from point A to point B. Okay. So, we were given our weight as being equal to 40 pounds. Alright, and it's going along the negative z-axis, so we can define our weight vector like that. And then for the rest of our, so we know in order for point A to be in equilibrium, we know our resultant force has to be equal to 0, and that's equal to the sum of all of our forces on the system. So that would be equal to the sum of force TAB plus the force TAC plus the force TAD plus our weight has to be equal to 0. So we're going to write TAB, TAC, and TAD in Cartesian form. So we're going to start with TAB. Alright, so from point A to point B, the cable goes along the x-axis 3 feet. It goes up in the z-axis 8 feet, and it goes along the negative y-axis 4 feet. So we can use those dimensions that the problem gives us to calculate the percentage of the force TAB that would go along the x, y, and z axes. So in order to do that, what we will do is we'll multiply the magnitude of vector TAB times the unit vector from point A to point B. So we're going to calculate UAB. Alright, so we know that UAB is equal to RAB divided by the magnitude of RAB. So we know that RAB is just equal to RB minus RA. The nice thing in this case is RA is equal to 0, so we can ignore it. Alright, so we're just left with RB. So RB is just the coordinates of point B. So point B is minus 3 feet along the x-axis. It is minus 4 feet along the y-axis, and it's a positive 8 feet along the z-axis. So if we square all these terms, we'll get 9 feet squared plus 16 feet squared plus 8 feet squared, which is 64 feet squared. So if we add these all together, we'll get 25 plus 64, which is like the square root of 89. If we divide the square root of 89 by our x, our y, and our z components, we'll get our individual components. So it would be TAB times negative 0.31800 for our x component. Our y component would be equal to minus 0.42400 times j plus our z component, which would be equal to 0.84800. K, and all of these should have I should include a TAB term in all of these. Right. So once we have, we have TAB defined as a Cartesian vector. So we need to define TAC and TAD as Cartesian vectors. TAC, which is going to be equal to the magnitude of TAC times UAC. Now, if we look at the dimensions of our system here, the length of AC is the same as the length from AB. The only difference between point B and point C is point C is has a positive y coordinate, while point B has a negative y coordinate. So the position vector is going to be the same as the unit vector will be the same as that of the unit vector for AC will be the same as the unit vector for AB, except for the y component, which is going to be positive instead of negative. So we can write this vector as being equal to minus 0.31800 TAC times I plus 0.42400 TAC times J plus 0.84800 TAC times K. Right. TAD, alright, we could also write as being equal to TAD UAD. Alright, in this case, UAD is equal to R of D minus RA divided by the magnitude of RD minus RA. The nice thing here is that point D only has a y coordinate, or an x coordinate I should say, so its unit vector is going to end up being equal to the length of AD I plus 0j plus 0k divided by the length of AD squared times the square root of plus 0 squared plus 0 squared. This ends up just being equal to 1I plus 0j plus 0k, alright, times times TAD. So what we end up getting is just TAD only has an x component. Alright, so and then the last thing was our weight, which we already defined at the top equation here. So, or at the top of the screen. So we can now add these all together to get our resultant force. So we'll have all of our x components, all of our y components, and all of our z components. Alright, so if we add all of our x components together, what we end up getting is we get minus 0.318 FB minus 0.318 FC plus FD. Alright, for the y component, we'll get minus 0.42400 FB plus 0.42400. Sorry, this should be TAB. This should be TAC, and then we have to have minus TAD here. Alright, and then this will be TAB, and then this will be TAC. And then for the Z components, we'll just get 0.848 TAB plus 0.848 TAC minus our weight of 40 pounds. All right. So what we can do here is we're going to first look at the y component of our resultant vector and set that equal to 0. So that's going to be this term here. So if we set that equal to 0, what we end up getting is we get 0.42400 TAB is equal to 0.42400 TAC. We can then say that TAB must equal TAC for the particle to be in equilibrium. We can then go on to sum the forces in the y direction and set that equal to, or in the z direction and set that equal to 0. Alright, so if we do that, what we'll end up getting is 0.848 TAB plus 0.848 TAC, which I'm going to substitute in for TAB using this equation here. Minus 40 pounds is going to be equal to 0. So what we'll end up getting is 1.696 TAB is going to be equal to 40 pounds. So if we divide by 1.696, we get TAB is going to be equal to 23.585 pounds. And then we would also say that TAC would also be equal to 23.585 pounds. All right, we can round these both to be approximately 23.6 pounds. Alright, and then for the last part, we can sum all of our forces in the x direction and set that equal to 0. So if we do that, we would get, so that's this equation on the left-hand side of our resultant vector. So if we do that, what we'll end up getting is we'll get 0 is going to be equal to minus 0.318 TAB minus 0.318 TAC minus TAD. Alright, so we add I'm sorry, this should be a plus up here. TAD is going along the positive x-axis. So we can rearrange this and we get TAD is going to be equal to 0.636 times TAC, which we know is equal to 23.585 pounds. All right, and we end up getting 15.000 pounds, or 15.0 pounds for TAD. All right, so to recap what we did here, is we first drew our free body diagram. Once we had our free body diagram of the particle at point A, we defined our resultant vector and set it equal to 0. We defined each of our component forces in Cartesian form using the unit vector for each force, and once we had our resultant force, we then just set each of the x, y, and z components equal to 0, and we were able to solve for our three unknown forces.